2 years after receiving the Nobel Prize in 1921, Einstein gave a speech at the 1923 Nobel Prize ceremony, saying, "A person who seeks a theory of everything cannot happily continue his life assuming that there are two completely independent laws in the universe." He is actually talking about himself here. From the man who discovered the theory of general relativity, he is still not happy. He wants more. He wants to reach the nirvana of science. Yes, he is talking about the ultimate goal of science. What is the ultimate goal of science? Throughout history, many scientists have worked on different theories. There are still many different studies going on in many different fields. But those who follow me and read between the lines of all the theories I mentioned will have noticed this. They are all connected. Everything is related at some point. That is the ultimate goal of science, to find the point where everything, all theories, converge. They call this unification. Think of all the groundbreaking scientists. Isaac Newton, he simplified and unified the theory that governs the movements on Earth and all celestial bodies. Michael Faraday and James Clerk Maxwell, electricity and magnetism. Albert Einstein, matter, energy, and time. He was ushering in an era of unification. He was simplifying history. But Einstein was uncomfortable with this because in the 1920s, two forces were known to control the universe: gravity and electromagnetism. These two forces appeared completely independent of each other, and the universe was governed separately by these two entirely independent forces. But that shouldn't be the case. Einstein came to this conclusion especially after receiving a letter from Theodore Kaluza in 1919. It was one of the letters that excited him the most. Remember, Einstein had added space-time to the universe, which was known to be three-dimensional until then, and had mapped out a four-dimensional universe for us. Kaluza said, "Why not five?" In other words, he thought that by using Maxwell's equations of electromagnetism, general relativity and electromagnetism could be combined, and the theory of everything that everyone throughout history had been striving to achieve could be revealed. Einstein guided Kaluza on this subject and pioneered the publication of his theory in 1921. However, there were some problems. We could test space-time and the three spatial dimensions in some way. We could neither experience nor see this fifth dimension. It was impossible to test. At this point, in 1926, Oscar Klein stepped in and said that this fifth dimension must be circular, and the famous Kaluza-Klein theory was born. The reason we couldn't see it was that this fifth dimension was very small. This is actually why when you look at a tornado from hundreds of meters away, you see it as a line. We cannot comprehend a dimension, a thickness. With this fifth dimension, Einstein thought he could combine gravity and electromagnetism, and from the early 1920s until his death in 1955, he would try to prove this and write a theory of everything. But in the meantime, things had gotten complicated in the world of physics, and quantum mechanics was shaking everything up. As you know, Einstein never liked this mechanics. He was sure it had a flaw. Don't get me wrong, he didn't reject it. He just couldn't accept its incomprehensibility. And in fact, he believed that by combining electromagnetism and gravity, he would also find a solution to the incomprehensibilities of quantum mechanics. So in his home in Princeton, he closed his eyes to everything that was happening, to quantum mechanics, and began to work. Perhaps this was one of his biggest mistakes. He had achieved incredible things in his time, but he had officially started to be treated like a grumpy old man. The scientists weren't wrong, but Einstein was also very unlucky, because with quantum mechanics, he would begin to learn many new things. Very, very new things. By the 1950s, we would encounter new forces governing the universe previously thought to be governed by electromagnetism and gravity, nuclear forces. While gravity and electromagnetism are forces that affect daily life and govern the universe, nuclear forces govern the world of subatomic particles. And nuclear forces are divided into two. The first is the strong nuclear force. As the name suggests, it is the strongest force in the universe. It may seem strange, but gravity, the force that keeps the Earth orbiting the Sun and everything on Earth in place, is the weakest force in the universe. We've already explained that gravity is the curvature of space-time. Anyway, the strong nuclear force is the force that holds together the quarks that make up protons or neutrons. The thing is, the quarks that make up protons or neutrons have the same electric charge. Particles with the same electric charge tend to repel each other. Think about what happens when you bring two positive magnets close to each other. This is the force that binds these particles, that holds them together, the strong nuclear force. This force is also carried by the gluon. That's why it is effective over very short distances, within the diameter of a proton. But it is so strong that the strong nuclear force between two quarks is thought to be equivalent to the gravitational force acting on a 16-ton mass on Earth. Therefore, it is theoretically impossible to separate quarks from each other. Free quarks have not been observed. Even though it has not yet been proven, there is a perception among physicists today that, let's not bother, we can't separate quarks. In addition, there is also the weak nuclear force. This also concerns subatomic particles. The weak nuclear force is approximately 1/1000th of the strong one, and its fundamental effect is to change the types of quarks and leptons. Why are we talking about this? Without this force, fusion, which provides the sun's energy, i.e. the reaction of nuclei merging and radioactive decay, would not occur. As you may have noticed, we are talking about leptons, quarks, gluons. We are talking about a lot of new particles, and we will talk about many more in the future. But until the 1950s, it was thought that atoms consisted only of protons, neutrons, and electrons. But the particles that make up atoms themselves are made up of dozens of other particles, and gravity and electromagnetism have no effect in the universe of these particles. That's why Einstein was unfortunately working for vain. We can actually understand where Einstein went wrong with an example: black holes. Yes, think about black holes. They are among the heaviest formations in the universe, but they are very, very small. So will we examine black holes with the theory of general relativity because they are so heavy, or with electromagnetism because they are so small? The answer to this question creates a paradox and reveals the need for a much more comprehensive theory. As Einstein said, it was illogical to describe the motion of an apple with one law and the motion of subatomic particles with a completely different law, because these four fundamental forces we have should actually be one. How do we know? From the Big Bang. Rewind time. Think of it like a movie. If you rewind the film and go back to the Big Bang, the universe was a tiny point 1 second before that explosion. A point containing an incredible force. Gravity, electromagnetism, and nuclear forces were all together within that point. They were all actually one. A second later, they all separated into distinct forces. At least that's what we think with our limited minds. They're still somewhere, beneath even subatomic particles. These forces are performing an incredibly beautiful concert with a magnificent melody. Don't forget this analogy. Don't forget the music. We'll be back. It was in the 1960s that the foundations of the theory that would unite everything, explain everything, from the orbit and gravity of Alpha Centauri to the energy possessed by neutron stars, from radio waves to quantum computers. The theory of everything began to be laid. A few years after Einstein's death, we now had gravity on one side and electromagnetism, strong and weak nuclear forces, on the other. In 1968, a physicist named Gabriele Veneziano, who now works at CERN, was researching the strong nuclear force when he started reading an old math book. In this book, he came across a formula related to the gamma function written by Leonhard Euler almost 200 years earlier. This formula, that had been gathering dust on shelves for 2 centuries and considered one of the wonders of mathematics, was so universal that it actually explained nuclear forces even before atoms existed. It was an incredible event. Gabriele Veneziano, who interpreted Leonhard Euler's formula, would become very well known in this field. But this formula would become so famous that it would be passed from hand to hand, and everyone would have an opinion about it. One day, this formula would come before another young physicist, Leonard Susskind. The name may sound familiar. One of the most important physicists of modern times. Why is he important? Because in a way, because of this formula written by Leonhard Euler centuries ago. Because Susskind sees something in this formula that no one else sees. While everyone else sees particles as points, as balls, Susskind reads something very different in the subtext of Euler's formula. He sees something like a rubber band, a string, more precisely, a string. A string that twists, bends, curves left and right, vibrates. Things vibrating in a universe beyond particles, smaller than particles themselves. Yes, I think everyone now understands where we're slowly heading. There are a few more topics we'll discuss first, but we're slowly coming to the melody I've been hinting at from the very beginning. I think we can start talking about the music of the universe now. I can hold off a little longer, but we'll be talking about many other things soon. A crazy, crazy theory that will make quantum mechanics seem very innocent. In fact, let me put it this way. There was this quantum madness that lasted from the early 1900s to the 50s, 60s, and beyond. Arguments, denials, disbelief. I think we are right in the middle of such a period now. Somewhere, the Max Plancks, Niels Bohrs, and Einsteins of modern times are working on a theory that could explain the universe with a single formula, a single theory. Yes, I'm talking about string theory, M-theory, the theory of everything. Stay tuned, and as always, until we meet again, I'm glad you're here. With love.